We will look into a nice property of discrete random variables, but you'll notice that this property will carry on to other variables also. So this is how we linearly transform variables and how it impacts things such as the mean and the standard deviation, or the expected value and standard deviation. So we can pause this, have a go at this investigation. Try out what happens when you transform a variable x to another variable y, and see how the expected value changes based on that. So based on the experiment, you should get certain properties, but before we start, it's useful to know some of the properties of expected value specifically. So if you have a constant k and you are trying to take the expected value of a constant, then the answer is just the constant itself. You can do a small proof of this if you want to, which means that if I'm taking the expected value of the constant times my variable, then the answer is just k times my expected value. And if I'm taking the expected value of two functions, two separate things, I can take the expected value of them separately. So it's like expanding out the expected value in here. So these are useful properties that we're going to rely on for the proofs later. So from the investigation, you would see that if your variable is being transformed, if x is being multiplied by a constant and a number is being added to it also, then the expected value would also change as such. You will multiply this by the same value and add. If you recall, this was already discussed in a lesson on measures of dispersion. You can go back to that video, watch it. There is a section at the end about the transformation of variables, and the same thing has happened with the mean. If your variables, if your data has been multiplied by a value, and then you're adding a number to it, then the same thing will happen to the mean. And remember, expected value is the mean. So the linear transformation of the mean, and this applies to all random variables, not just discrete, is that the constant you're multiplying with will multiply with the mean, and whatever you're adding will also add to the mean. What about variance and standard deviation? How do those come into the random variables? Well, we can apply the same definition of variance that we know from normal statistics and use it in random variables. So this is a definition that we're going to use for variance, which is that it's the this definition is each value minus the mean, and then we square that. So if we define mu to be the expected value, because that's the mean, so the variance is basically taking the x minus the mean being squared. So this is what we're calculating. And then if I square this, expand the bracket, I get x squared minus 2x mu plus mu squared. And then again, using the properties of expected value, I can expand this out, noting that if I take the expected of 2x minus mu, I can take the 2 and the mu out because these are constants. So we're using this property and this property. I can take them out, so I'm only left with e x squared minus 2 mu e to the x plus e mu squared. So, and again, I will use this definition that mu is the expected value, and e mu squared is just mu squared. So we have, again, this is like the constant property. So I can rewrite these two as e of x squared minus 2 mu squared plus mu squared, which will give me e to the x squared minus mu squared. And again, we know that mu is e to the x, so this gets replaced back with e to the x being squared. Another way of writing this is to say it's e to the x being squared on the inside minus e to the x being squared on the outside. this is the definition for variance that you will rely on. And if I take the square root of this, it will give me the standard deviation. So in summary, this is what you need to know. The expected value of random variables is just mu, or we multiply the x value with the probability and we add them up. We know that already. And variance of random variables is basically taking the x value squared, taking the expected value of that minus the original expected value and squaring that. How do we find this? E to the x squared. E to the x squared is the same thing as, it's the same process as finding the expected value, but instead of multiplying each x value with the probability, we'll multiply the square of each x value with the probability and add them all up. And if I need e of x being squared, I just find the normal e of x and I square it. Once you have the variance, if you square root it, you will get the standard deviation. So this is the standard definition for expected value and variance that is applied, again, to all random variables. So notice that it says random variables and not just discrete. So let's have a go at this. We're going to practice it on discrete random variable right now. So you have two disks that are drawn with outer replacement from a box containing 4 blue disks and 3 red disks. If the event x is the number of blue disks drawn, can you construct a probability distribution table? So can you pause the video and try creating the table, just so you can make sure you know how to practice, and at least complete part B also, e to the x. And I would encourage you to find the other values also if you could before I reveal the answers. So we calculate the probability. You can use a tree diagram if you want to, or you can list them out if you want to, of how all the probabilities are obtained. So the probability of getting no blue disks would be 6 over 42, 1 disk would be 24 over 42, 2 disks will be 12 over 42. So now I can calculate the expected value using the normal formula by multiplying these values together and then adding them up. So we can see here I'm multiplying 0 with the 6 over 42, 1 with the 24 over 42, and 2 with the 12 over 42. And then I'm adding them up and I get 1.14. That's the 3 significant figures. Now if you need e to the x squared, the way you do it is you do the same process, but these values will now be squared. So if you notice now we're doing 0, well 0 squared is just 0, 1 squared is just 1, but then 2 squared is 4. So instead of 2 times 12 over 42, you're going to do 2 squared times 12 over 42. Careful, you're not squaring the probability, you're squaring the x value. And that will be 1.71. If I want the variance, again, I'm using the formula for variance. So that would be e to the x being squared on the inside minus e to the x being squared on the outside. So I'm taking what I squared on the inside, which is 12 over 7, and I'm taking away the expected value, 8 over 7, but that's squared, so 0.408. This will be the variance, and if I want the standard deviation, I just take the square root of that, which is 0.6393 significant figures. So you can practice questions here on how to find these values, and then we'll dive into more properties. So further standard results, we already talked about how linear transformation impacts the expected value, but how would it impact the variance? Well, the same way, if we go back to the properties of expected value, so remember these properties, and this property. So what's the equivalence when we deal with variance? And again, if we deal with variance, the square root would just be the standard deviation. If your a is a real number, then the variance of a would just be 0. And we can look at the proof here. If I just use the definition of variance, it's e to the a squared minus e squared a. Well, a squared is just going to be a squared. And e to the a is just a, but then I'm squaring it, so it's again a squared. And I'm subtracting them, so it's a 0. Well, what if I multiply my variable within A, what happens? Well, I can then still apply the formula. So I'm doing AX being squared minus the expected value of AX, all of it being squared on the outside. And this will simplify to A squared, and then X squared on the inside. This will also simplify to A squared, E squared, X. You can think of this transformation a bit more. I can then expand A squared out, and I would get in the inside, I would factor out A squared, and what I get inside the bracket is the equivalence of the variance. So basically what I end up with is that if you multiply your variable X by a constant, then it's the same as squaring that value multiplied by the variance. And recall, again, going back to the lesson on linear transformations when we did measures of dispersion, this was the same linear transformation. We did mention that if your data is being multiplied by a certain value, then the variance of the data will be multiplied by the square of that value. So this is not a coincidence here. And if we combine full linear transformation, so what if I'm multiplying and I'm adding, again using the proofs, you would end up with this result, is that if you're multiplying and adding, the addition does not impact the variance, it's only the multiplication that does, and you are multiplying with the square of it. So in summary, this is what you need to know. The linear transformation of expected values, if you're multiplying your variable by a scalar and adding, then the expected value would also behave the same. For variance, it's only the multiplication that impacts it, and you square it. For standard deviation, you take the absolute value, because standard deviation has to be positive, and you multiply it by the standard deviation. Or you can find the variance and then square root it to get the standard deviation. So these results are not new. You've seen them before, but we're just writing it in a more sophisticated manner for random variables specifically, rather than a normal statistical data set. So let's practice with this. So if you have a random variable X, we don't know what type of variable. It could be discrete, it could be continuous, doesn't matter, because these features apply to all. And it has a mean of 8.1, a standard deviation 2.37. If I have a new variable y, and y is obtained by multiplying all the variables x by 4 and subtracting 7, what's the mean and standard deviation of y? So this is quite easy to compute. The new mean of y, or we can say the expected value of y, is going to be 4 times the expected value of x minus 7, which is 4 times 8.1 minus 7, which gives us 25.4. So directly applying it there. And again, you've seen this before, but we're just doing it in for random variables. And then the standard deviation, you can use this notation, you can use variance if you want to, and then square root it. For the standard deviation, it's just going to be the absolute value of what you're multiplying here, which is just 4, times the standard deviation 2.37. If I'm looking for variance, then I would, if I had the variance here, for example, then you need to multiply by 4 squared, remember that. So this would be 9.48. And that's it. It's quite simple, straightforward. You can practice questions here, see how the transformations apply so you're more fluent with it. And then just to clarify that you can use technology to find the standard deviation of discrete random variables. You just enter your x values in L1 and the probabilities in L2, and then you complete a one variance stat. And actually remember these values that you used to get but you never used. Well, the first value, sorry, it's meant to be this here, is your expected value. You can use it as your expected value. The sum of x squared, this gives you the x squared value, and then the standard deviation will be given by this. So it's quite useful to use the calculator for these. You can also check. You can also find the variance through these, but the calculator already gives you the values in there. So you can also take, just to clarify, so these both would be expected values, but you can take e of x, remember the formula for variance, so you would take, sorry, this one first, 6.97 minus 2.39 squared, and that will give you 1.2579, so that would be the variance. And if you actually square root to this, it will give you exactly, you can check, 1.12 and so on, 156.141. So that's the standard deviation.